Welcome to ReneEnergy.com on YouTube, the hub for all things renewable energy and sustainability. Hey there, clean energy enthusiasts. Welcome back to Renee Energy's YouTube channel. Today, we're diving into the key concepts behind green hydrogen projects. Instead of focusing on complex formulas, we'll explore the fundamental ideas that drive this exciting technology. These concepts are the building blocks that engineers, project developers, and policymakers use to shape the future of clean energy. So, let's unpack the essentials of the hydrogen revolution. Electrolyzer efficiency. At the heart of any green hydrogen project is the electrolyzer. This device uses electricity to split water into hydrogen and oxygen. Efficiency here is all about how much of the electrical energy we put in actually ends up stored in the hydrogen we produce. Think of it like a funnel. We want as much of the energy to make it through as possible, with minimal losses. Higher efficiency means we're making better use of our renewable electricity, which ultimately leads to more cost-effective hydrogen production. It's not just about the technology itself. Factors like temperature, pressure, and the purity of input water can all affect efficiency. Modern electrolyzers can achieve efficiencies of 70 to 80%, but there's ongoing research to push this even higher. Every percentage point improvement in efficiency can translate to significant cost savings over the life of a project. Hydrogen production rate. This concept is pretty straightforward. It's about how much hydrogen we can produce in a given time period, usually measured in kilograms per day. It's influenced by the size of our electrolyzer, how efficiently it's running, and how long we operate it each day. Understanding production rate is crucial for matching our hydrogen supply to demand and for sizing our overall system. It's not just about maximizing production. We need to balance it with the availability of renewable energy and the demands of our end users. For large-scale projects, we might be talking about production rates of several tons per day. But even smaller, distributed systems producing a few hundred kilograms daily can play a crucial role in local energy ecosystems. Water consumption. Water is the raw material for hydrogen production through electrolysis. We need to know how much water we'll use to produce a certain amount of hydrogen. This helps us plan our water supply and treatment systems. It's worth noting that while hydrogen production does use water, the amounts are generally modest compared to many other industrial processes. Typically, we're looking at about 9 liters of water to produce 1 kilogram of hydrogen. In water-stressed regions, this concept becomes particularly important. Some projects are exploring the use of seawater or wastewater as input, which adds complexity to the process but could make hydrogen production viable in more locations. Renewable energy required. To keep our hydrogen green, we need to power our electrolyzers with renewable energy. This concept involves calculating how much renewable electricity we need to produce a given amount of hydrogen. It's not just about matching total energy, we also need to consider the intermittent nature of many renewable sources and how that aligns with our hydrogen production needs. This is where the idea of hydrogen as an energy storage medium really shines. We can use excess renewable energy to produce hydrogen, effectively storing that energy for later use. The amount of energy required is significant, about 50 to 55 kilowatt hours to produce 1 kilogram of hydrogen. This means that large-scale hydrogen production will require substantial renewable energy capacity. Levelized cost of hydrogen, LCOH. This is a crucial economic concept. LCOH represents the average cost to produce a unit of hydrogen over the lifetime of the project, taking into account all costs, from initial investment to ongoing operations and maintenance. It's a key metric for comparing different hydrogen production methods and for assessing the economic viability of projects. LCOH is typically expressed in dollars per kilogram of hydrogen. Currently, green hydrogen costs are higher than fossil fuel-derived hydrogen, but they're falling rapidly. Projections suggest that green hydrogen could reach cost parity in many regions by 2030, driven by decreasing renewable energy and electrolyzer costs. 1. Carbon intensity of hydrogen. While we're aiming for zero-emission hydrogen, it's important to account for any emissions associated with the entire production process. This might include emissions from manufacturing equipment or transporting hydrogen. Understanding carbon intensity helps us ensure our hydrogen is truly green and can help in carbon accounting and regulatory compliance. It's typically measured in grams of CO2 equivalent per megajoule of hydrogen. For green hydrogen, the carbon intensity is very low, typically less than 1 kilogram of carbon dioxide equivalent per kilogram of hydrogen produced. Compare this to gray hydrogen from natural gas, which can emit 9 to 12 kilograms of carbon dioxide equivalent per kilogram of hydrogen produced. Electrolyzer stack degradation. Over time, electrolyzers become less efficient. This concept involves understanding how quickly this happens and how it affects our hydrogen production over the project's lifetime. Accounting for degradation is crucial for accurate long-term planning and maintenance scheduling. Modern electrolyzers might see efficiency losses of 0.5 to 2% per year. This degradation isn't just about reduced output, it also affects the economics of the project. As efficiency decreases, we need more electricity to produce the same amount of hydrogen, increasing our operating costs. Compression energy. Once we've produced hydrogen, we often need to compress it for storage or transport. This process requires energy, which we need to factor into our overall energy calculations. Understanding compression energy needs helps us optimize our storage and distribution systems. The energy required depends on the initial and final pressures. Compressing hydrogen to 700 bar, typical for vehicle fueling, can consume 10 to 15% of the energy content of the hydrogen. Innovations in compression technology, like electrochemical compression, are aiming to reduce this energy requirement. 1. Storage capacity. Hydrogen has a low volumetric energy density, which means we need relatively large storage volumes. This concept involves calculating how much space we need to store a given amount of hydrogen. It's crucial for designing storage systems and for projects where we need to store large quantities of hydrogen over time. Storage options range from high-pressure tanks to underground caverns for large-scale storage. The choice of storage method affects not just the space required, but also the overall system cost and efficiency. Liquefaction of hydrogen, for instance, allows for higher storage density but requires significant energy input. Pipeline capacity. If we're transporting hydrogen via pipeline, we need to understand how much we can move through a given pipe size. This involves complex fluid dynamics concepts. Understanding pipeline capacity is crucial for designing distribution networks and for projects involving long-distance hydrogen transport. It's not just about volume. We need to consider factors like pressure drop over distance and the potential for hydrogen embrittlement of pipeline materials. Some projects are exploring the use of existing natural gas infrastructure for hydrogen transport, which adds another layer of complexity to capacity calculations. Fuel cell efficiency. When we use hydrogen in fuel cells to generate electricity, we need to understand how efficiently this process occurs. This efficiency affects the overall usefulness of hydrogen as an energy carrier. Fuel cell efficiencies typically range from 40 to 60%, which is actually quite good compared to many conventional energy conversion technologies. When we consider the potential for using waste heat from fuel cells, the overall system efficiency can be even higher. Understanding fuel cell efficiency is crucial for applications like hydrogen vehicles or stationary power systems. Project Net Present Value, NPV. This is a fundamental concept in project finance. NPV helps us understand the total value of a project over its lifetime, accounting for the time value of money. It's a key metric for deciding whether a project is financially viable. A positive NPV indicates that the project is expected to be profitable, considering both the initial investment and future cash flows. For green hydrogen projects, calculating NPV can be complex due to uncertainties in future energy prices and potential regulatory changes. However, it remains a crucial tool for project evaluation. Internal rate of return, IRR. IRR is another crucial financial metric. It represents the expected annual return on investment for the project. It's often used alongside NPV for project evaluation. For green hydrogen projects, target IRRs might be higher than for more established technologies, reflecting the higher perceived risk. However, as the technology matures and becomes more mainstream, we might see IRR expectations aligning more closely with other renewable energy projects. Payback period. This concept tells us how long it will take for a project to recoup its initial investment. It's a simple but useful metric for assessing project risk and appeal. For early green hydrogen projects, payback periods might be longer due to high initial costs. However, as technology improves and scales up, we're seeing these periods shorten. Some optimistic projections suggest payback periods could fall to 5 to 7 years for optimal projects by 2030. 1. Sensitivity analysis. This involves understanding how changes in various inputs, like electricity prices or equipment costs, affect our project outcomes. It helps us identify which factors have the biggest impact on project success. For green hydrogen projects, key sensitivities often include electricity prices, electrolyzer costs, and capacity factor. Understanding these sensitivities helps project developers focus their efforts on the most impactful areas for improvement. Conclusion. And there you have it, folks. These are the key concepts underpinning green hydrogen projects. Understanding these ideas is crucial for anyone looking to dive into the world of green hydrogen. Remember, while the math behind these concepts can get complex, the basic ideas are what drive innovation and progress in this field. Whether you're optimizing production, designing storage systems, or evaluating project economics, these concepts form the foundation of successful green hydrogen initiatives. It's exciting to see how these concepts are being applied in real-world projects. From massive offshore wind-powered hydrogen production in the North Sea to small-scale systems providing energy independence for remote communities, the applications are diverse and growing. As we look to the future, these concepts will continue to evolve. Advances in materials science might lead to more efficient electrolyzers. Innovations in storage technology could change how we think about hydrogen distribution. And as our understanding of the hydrogen economy grows, new economic models might emerge. One of the most exciting aspects of green hydrogen is its potential to decarbonize sectors that are difficult to electrify directly. Heavy industry, long-haul transport, and high-temperature industrial processes could all be transformed by the availability of clean, green hydrogen. Moreover, green hydrogen plays into the broader concept of sector coupling, the idea of integrating our electricity, heating, and transport systems for greater overall efficiency. Hydrogen could be the key that unlocks this integration, providing a flexible energy carrier that can flow between these traditionally separate sectors. If you're excited to learn more about how these concepts apply in real-world projects, don't forget to check out our comprehensive green hydrogen development and financing course at renewenergy.com. We dive deep into practical applications and case studies, giving you the tools to turn these concepts into reality. The future of energy is green, it's hydrogen-powered, and it's built on a solid understanding of these fundamental concepts. Keep learning, keep innovating, and together, let's build a sustainable energy future. Until next time, this is Renee Energy, where we're unpacking the building blocks of clean energy. Remember, every step towards understanding these concepts is a step towards a cleaner, greener world. Whether you're a student, a professional, or just an enthusiast, your engagement with these ideas contributes to the momentum of the clean energy revolution. So keep asking questions, keep exploring, and who knows, you might be the one to develop the next big innovation in green hydrogen technology. Thanks for tuning into the renewenergy.com YouTube channel. We trust you found this episode and